Tennessee, Knoxville, and Shekhar Ramanathan from Dartmouth, who are expert on quantum information science. So what we actually tried to do, there were beautiful things in quantum information science that were done, and unfortunately, that's mostly mathematics. It works on perfect systems, you know, 1 and zeros. But once you put materials, all bets are off. And, you know, it took us 5 years to put this together, to connect the two worlds, okay? So, you know, why do we care about quantum stuff? Well, this is just, you know, I had to prepare some talk, and we call this old quantum, you know, all the quantum things that we have, and we're not really interesting, but, you know, most importantly, none of medical imaging would work without quantum mechanics. And then, you know, we wouldn't have our iPhone, right? That's the most important thing, because you would not be able to make a switch to turn on 5 gigahertz frequency if you didn't actually use quantum effects. And of course, nowadays we're all chasing all these beautiful things, 100% secure communication, you know, quantum computers that can do wonders, and quantum internet, but that's a dream. So in order to, just like, you know, the old quantum stuff, in order to actually reach these goals here, you need to have the real materials, right? So you need to be able to actually produce these resonant tunneling diodes. You know, you need gallium arsenide, okay? But you need a material with the right properties that then you can harness and, you know, make some revolution. So, you know, the problem is that we don't really know what the material properties are. So this is kind of something I borrowed from one of Stephen's talks, actually, a laundry list, what we do, okay? Somebody makes a material, and, you know, I'm grateful to my colleagues who invent new materials. And, you know, we see what is the crystal geometry, and whether it's an insulator, we measure resistance, we measure response, right, to something. You apply voltage, you apply magnetic field, and you see what the response it is. And, you know, then you start complicating things, and then these are the theoretical tools that we have on our disposal. Very few BCS, fractional quantum Hall effect, I think have, you know, the solution, the wave function, the solution for the ground state. All the other stuff are, you know, beautiful approximation, it works in the absence of better things. But, you know, what we would really like to do is to figure out, if somebody makes a material, can I do a measurement and tell you what the Hamiltonian, right, it is? So I call this biometric passport, right, of my material. And if I knew what the Hamiltonian is, then I would be able to, you know, figure out how to use it in a right way or manipulate it the right way. That's another difficult thing. So what is the real problem? You know, why don't we have Hamiltonian for every new material that, you know, Professor Plum makes here, okay? Or anything else, any of us, right? Well, it comes with, every material is quantum, right? Because you have to pair up electron, there's Pauli exclusion, so I'm not gonna even repeat this quantum material. It's an oxymoron. It is, everything is quantum when you start putting materials together. And, you know, there's just no instrument, right, that will allow you to take a picture of this quantum state. Meaning, and it's basically where fundamentally, right, this is just an example of a wave function, right? This is for a reason complex quantity, or, you know, there's this phase here, which is a complex number or imaginary number. It's not for nothing that it's called imaginary. It means you cannot measure it. So the only way you could figure out this phase here, or what really encoded in this quantum state, is come up with some clever way of producing an interference experiment where you could actually measure some relative phase, okay? So there's absolutely nothing that allows you to be able to probe the wave function. I mean, it's just what fundamentally, right? So we can measure these eigenstates. So meaning in an experiment, right, what I can actually measure, what we usually do, all of us in condensed matter physics, we measure excitations, you know. What varies is, depending on what technique we use, we measure, you know, it depends what energy scales we probe and, you know, what momenta we probe. But in the essence, what we do is measure these excitations, and we can get an information about the energy eigenstates. But that's it. Or we can actually get a response to something, like, you know, we tweak the voltage, and I can measure conductance of my device, and so on and so forth. But I can never take a picture of that. However, I want to remind you, for those of you what I said, we can induce some kind of interference device is that, well, if I have this, qubit or, my little state, an arrow pointing up, spin, the simplest of all, just pointing up or down. Well, there's something we can do that you can produce a unitary operator to speak mathematical language, and that operator can involve this quantum state. And so if I can cleverly evolve this in time, maybe I can induce some interference and hopefully get some more information about what is a true quantum state of my, material. Now, this is all great. There's something else that makes quantum so powerful, or, and that is not just to know the Hamiltonian or this, wave function, whatever it is that describes my quantum state, but quantum states are so powerful because of entanglement property. And what that means, basically, if I tweak one part of my material somewhere here, then somebody else up here in space would actually instantaneously know about that, right? And so that's very useful for secure telecommunication and so on and so forth. Here, all these little Alice and Bob that you see in your textbooks about telecommunication, it works with a single photon, okay? You can do that. Once you put up, Avogadro number of electrons, or even 3 or 4, things become complicated. We don't know how to define entanglement, okay? And so there's our cartoon. This is as far as I can go, and I thank my colleague Leo Lee, if he's here, for his beautiful graphics here. We actually talked about it, and Leo came up, this is how you're going to actually picture entanglement in a material. And as you can see, there are these spins here and electrons, and there are these connections, entanglement between particles, and you notice it's like all over the place and connects to different particles, and the number of particles involved in it is different. To just tell you that we have no clue how to deal with this. And, there are theorists in quantum information that will tell you that, there's no such thing as many-body entanglement, and people spend their life telling you what is it that you should measure in order to figure out what is the metric. We don't even know what the metric of this is, okay? So it's complicated, but it would be cool if, I could actually measure this, you see? Expectation value of this entanglement between, my material, okay? Yeah, thank you. So let me now go back to old-fashioned condensed matter physics, okay? So there's this thing that limits me from knowing exactly, intrinsic property of quantum mechanics that prevents me from really measuring the wave function of this state of material. But also, this is our old-fashioned condensed matter physics that, well, if we put interactions, Coulomb interaction between electrons, there is Avogadro number of them in every chunk of material, the problem is impossible to solve, right? We can't even solve 3-body problem, let alone, many electron problem, or there are very few solvable problems. And then, what gives you these topological properties, a lot of cool, as you notice on my previous picture, I had something like, we can have these very useful topological conducting states on a surface. Well, all of these topology, you can even read here, topological insulators, it needs a spin-orbit coupling. So it's one of the first ingredients to produce these states in a material. And what I mean by that, there's an entanglement between, or coupling between a spin, pure spin, the arrows that point up and down, and the orbital motion of electrons, or orbital degrees of freedom. And so to speak a technical language, spin is not a good quantum number. In reality, instead of talking about, spin like this, that we, in equations write, their coupling is written just by the product of 2 spins, you're dealing with something that looks like this when you account for the orbitals, where these colors just give you a spin density of, say, pointing up or down, or probability for pointing that way. And then, you can have these very complex orbital orders, and these are just some pictures of states that we studied. And the funny thing about them is that if you look, you see right here where, your lattice points are, this lobes, this multipolar is 0. So if you were to measure, say, magnetization of this state, you would find 0 on average, and a lot of other things. So it's a really tricky business how to measure this stuff. And, on top of spin-orbit coupling and interactions that we deal in real materials, there's, realization that if your lattice has, and I borrowed these pretty pictures from this review article, that, topology meets condensed matter physics or quantum materials, when you have a particular shape geometry of the lattice that so-called frustrates, meaning there are many possible ground states, you can get these very complex ordering. And, different colors here just tell you a different charge density on each of these plaquettes of the hexagon that produces, again, very different physical states. So, as I don't know if you can see these errors here, but you can actually get these two different shades at two different charge density states in which you break time reversal symmetry. So the way your charge flows is different, charge currents flow is different in the two cases, okay? So it's a mess, okay, in other words. So everything plays. The geometry of the lattice plays a role, interactions, entanglement between spin and orbital. And so how do we, pull this apart, okay? And, the problem with this is that, how to access this is that if you do these calculations or, study, these systems are intrinsically frustrated. What this means that you get many, many, many possible ground states, okay? So, their wave function is supposedly different if we were able to write it down, but the energy is the same almost, or very close by. And that means that if depending on what is my probe, whether I'm flipping a spin, whether I'm changing momentum in this direction or that direction of my probe, I would find very different answers. And, depending on the time scale of my measurement, we will conclude. So some of us work together to put the results together, and others argue, my probe is right and you're wrong, right? So because we all look at the different things, different aspects of the problem, right? And so, as I said, that's really the essence of all this, what we have available today. So, what is our approach? What is it that we can do different? And, approach in a nutshell, it's inspired by this. Okay, for once I actually wrote a wave function and not a cat here. But, a basic equation in a textbook on, quantum dynamics, right? So if somebody gives you a wave function at time equals to 0, you're basically at time equals to t, that function is going to evolve by this unitary operator here, t. And that operator looks like this. You see there's a Hamiltonian in there, right? Oof. And depending on what the relevant Hamiltonian of my system is, right, that determines the time evolution. And as you notice, it doesn't change the energy. It actually, this is imaginary here, so it changes the phase. So if we could manipulate this time evolution in a way, I could maybe control that, an interferometer, so to speak, right? Meaning that I can actually figure out what is this phase here. So that's what we're looking at. And, this is really what we want to do. So we're going to kind of give you an outline of where I'm going. I'm going to go into details, in a second. But what we want to do is to monitor the net phase that it's accumulated during control. Now, look, I suddenly popped the word nuclear spin ensemble and not electron. I talked about all electrons, right, materials. And the reason why I want to do that is that, electrons are here, and they are strongly coupled, and they are mass. So I don't know what their Hamiltonian. It's complicated, and you don't want to manipulate them with your probe. Okay, so you don't want to touch them. You want to be an observer, minimally invasive. And so there's a nuclei in materials are coupled through something called hyperfine coupling, overlap of the wave functions to electronic spin. Okay, only the spin part. We have experimental evidence for that, no theory yet. Okay, and basically the idea is that we know very well from, the technique has been actually discovered in 1945, nuclear magnetic resonance, and then in 1960s they reversed the axis of time, right? And then there were 3 Nobel Prizes actually in physics, chemistry, and medicine that came out of this technique, okay? So, we pretty much after 70 years, we have idea how to manipulate nuclei. We know to do that very well. And so the idea is that we can actually, I'm evolving now my nuclear wave functions, but their evolution is dictated strictly by, electronic Hamiltonian, by the properties of my electronic state, okay? So, and then, how do I evolve? How do I force something to, how do I manipulate? What I mean by that is that, well, we have radio frequency pulses, meaning resonant pulses for nuclear Zeeman splitting. I'll explain this. And what that does in, classically, if you think about it, that rotates your spin. That's, we know how to write the rotational matrices, right? And so these are the, we can rotate them and then let them evolve, okay? And we can stop that evolution. We can manipulate this evolution by simply RF pulse, by applying this rotational operator. And then you can produce funny effects, which I'll go to discuss. So this is kind of the essence of what we do. And then in the rest of the talk, because we have many nuclei in the material, the beauty of the nuclei are that they also sit at the lattice sites. So if you do your solid state physics, all the stuff we hate to calculate, the band theory, allowed momenta, your Brillouin zone and allowed momenta, right, of your electronic state is dictated by the lattice, right? So basically, when I manipulate my nuclei, they coherently couple to this allowed electronic momenta, which is also an advantage, okay? And, I have to switch my notation from these wave functions to density matrices because we're dealing with an ensemble, not a single spin, but there is Avogadro numbers. So technically, that's what I have to use. So there will be a lot of density matrices in it. So let me just go back one step to, now I kind of told you the theoretical idea behind this, but we need to connect everything to experiment, okay? And how do we do this? How do I build my, so this is kind of what do we do in standard NMR is that, we measure some spectra, some lines like this, and that gives us, so basically we have a nuclei, they are coupled through this tensor coupling, that it's really an overlap of the wave functions, two electronic spins. And when we do an experiment, that gives us an image of the local magnetic field probability distribution, meaning of really the arrangements of electronic spins around the nuclei. That's a kind of, we measure local magnetic field. So it's a real physical quantity, right? Again, there's no phase involved in its measurement. And, we can actually, it can be quite powerful. So you can figure out, these are just some graphics of very complicated spin arrangements that we've been able to figure out, from NMR and studying these spectra, okay? And you can also do another thing, which is you can measure excitations. You can measure these low energy excitations, energy, of electronic states. And if you have a nucleus that has a spin larger than 1/2, it's actually not a circle, but it's kind of elongated like a cigar. And that, it actually couples to electrical field gradients, electronic wave functions, electronic charge around the nuclear spin. And so, if you can use this to learn about, lattice deformation, charge distributions around nuclear spins, not just magnetic part, but the charge part. And it turns out that, if I have these suddenly my NMR line starts like this, it splits into, multiple depending on what the spin is. And so we can use that, again, to figure out charge degrees of freedom. So how does it all work in the lab? So, you applied magnetic field, and what you do is magnetic field splits the spins, right, into Zeeman levels, okay? But you need to detect that splitting, right? Because, I don't really know what this is. So what you actually do, what we do in reality is we need to disturb it from equilibrium, right? So we need to force these spins to flip up and down in order to be able to detect. So the way you change the direction of the spin is you have to apply, an operator that flips your spin is raising and lowering operator, which is linear superposition of x and y, meaning something that's perpendicular to your quantization field. And so you also have to conserve energy, right? So there are two things. And so this is why all you have to do is wrap a little solenoid around your sample and then apply the radio frequency or AC field, and that field frequency has to match to the Zeeman splitting, okay, so conserve the energy, but also has to be perpendicular to your applied field, the axis of the solenoid, this magnetic field that is created inside, so you can induce the spin flips. And, what happens, you would apply a pulse, you can actually control the time of this field that you're applying. And you can control the time in such a way that you assume that you flip your spins from Z to, you create a superposition in plus and minus, right? Superposition in a plane, and they would decohere, okay? Because this pulse can coherently flip them all into the plane, supposedly. And as they decohere, your magnetization along the axis of your solenoid is actually, the projection of these spins, it's decaying. So when I have a changing magnetic field, that induces current, and then that's what you detect in your coil, okay? And then, you get a signal like this, depending on where you are. You take a Fourier transform, and you obtain this spectrum, okay? So now, mathematically, what are you doing? This is very important so that we can actually, my signal in this language is, so we're detecting something, say, along the x-axis, something perpendicular to the applied field. That's the axis of the solenoid. And the way I can write this, well, it's my density matrix of my nuclei as a function of time, projected along the axis of, say, x, Ix, or I plus, I minus, whatever it is, okay? So it's a trace of that density matrix projected along the direction of this perpendicular, say, Ix, direction of the axis of my solenoid. That's how I would write it, mathematically in terms of quantum mechanical operators, what my, FID, free induction decay, what the NMR, simplest NMR signal is, okay? So now, basically, as you realize, the RF pulse, it's a rotational, that pulse that I talked about that flips the spin. So I only told you what direction, how I have to technically produce that, right? So I have to create the field which is perpendicular to the applied field. And then this is how, we represent mathematically the action of the pulse. It's a rotational matrix that it's applied to our density matrix of the nuclear spin ensemble, okay? And then to solve the time evolution, you basically have to solve this, equation of motion for the density matrix, okay? And we have two terms in a Hamiltonian. I apologize, this is too dark to see on a projector here, but the Hamiltonian that describes the coupling of the nuclear spins, this hyperfine, to the electron, it has two terms here. It has a simple Zeeman term that it just gives you the splitting of the levels, right? You put the nuclear spin, you put spin in a magnetic field, you'll have this Zeeman level splitting. And then this other term that corresponds to coupling to the charge degrees of electrical field gradients, charge degrees of freedom. On the back of your Sakurai textbook, there is 5 pages of math to show you that these electrical field gradients, you can actually represent this as a square in spin. So we have a term which is linear in a spin, and the coupling term that couples to charge, which is now quadratic in spin number, okay? And that's kind of something to keep in mind for later. And so this is something that we do, and I want to show this movie, which I hope. So what we actually measure is not just this free induction decay, but when I made a comment, we can reverse the axis of time, is we actually measure a spin echo. So if you look at this animation here, you apply what's called a 90-degree pulse, okay? I'm going to wait for that to happen again. Ta-da. Okay, they're all going to go up. See, all the spins are aligned by field. 90 puts it in plane, and then spins the phase, because each spin in a material feels slightly different magnetic field, slightly different Hamiltonian. That controls its phase, okay? And then after some time, you actually apply 180. You totally invert. You invert the axis of time of this time evolution, if you think of it that way. And, then if you wait enough, they will all, come together again and dephase again, and that's what we call echo. We generate this echo, okay? So to the pulses are represented, as I said, by these rotational matrices. And what happens when you apply this 180, it actually cancels any noise that it's accumulated, right? What spreads, what makes every nuclei rotate differently, evolve differently in time is the Hamiltonian, Zeeman-Hamiltonian. And Zeeman is linear in spin number. And so when I actually apply 180 pulse, or this operator here, you can easily show what that happens. It cancels any noise or dephasing that it's accumulated because of that interaction, okay? So let me now show what is the technique, what do we do, and what is it that can tell us something really fascinating about quantum materials. So this is the idea of the technique. We have two things. We have this Zeeman term, and then we have a coupling which is square in a spin number, 2 charge degrees of freedom to these electrical field gradients. And so what we do is now, we basically do a spin echo experiment. Okay, so this is a pulse sequence. Pi over 2, tau, pi, you wait and you get your echo. And what I'm actually showing you here is the time, right? So if you think each of these traces is a single echo for a given tau. And so we actually perform an experiment in which we, it's a 2-dimensional kind of space. And instead of looking at the classic echo, just meaning, what is the height of that echo, that's famous T2 in NMR, you actually now look at the signal, okay? You look at the height of the echo as a function of this other parameter, tau. So you acquire many, many echoes as a function of tau, and you look at the height of these echoes. And this is what I'm actually showing you here, okay? So mathematically, this is basically, I take my, then what is here is, it's the nuclear density matrix, how it looks after the time 2 tau, after this pulse sequence, after all the pulses were applied, the system evolves, and then all I have to do is to get what I measure is take the trace of, this density matrix projected along the axis of my detector, my coil, okay, Sx. We just choose X, okay, for simplicity. Could be Y, it doesn't matter, okay? So what we actually showing you here is the calculation, right? It's a simulation of what happens to your nuclear ensemble if, these are the terms here. This is the Hamiltonian that control this nuclear spin evolution. And this is what you get. This is the trace that you get as a function of tau, okay, this spacing. So this actually plots the signal magnitude at the time as a function of this time tau. So it plots the echo magnitude as a function of the different spacings, okay? So what you see here, these are just two, I want to show you. So here, for example, we have assumed that, Zeeman term is small, whatever it is, it doesn't really matter because you refocus that. And these two plots here show you two different cases for two different quadrupolar coupling, this quadratic term here, okay? And so if I look at the classical NMR, standard NMR, so just a spectrum, simple spectrum, I do a spin echo and I Fourier transform my echo, a single echo. This is what I get in these two cases, okay? So here, for example, I have, we have assumed that the Zeeman noise, or the spread in a Zeeman term, is, say, 100 kilohertz or something, and that's all you see here, actually 200 kilohertz, okay? And you see that here it just looks like a little Gaussian curve. Like, I have no idea that there is this quadrupolar coupling. If you increase this to 40, you start seeing a little bit of this wings here, okay, shoulders. So that's kind of resembles like, oh, I'm going to get this splitting, right? But this electrical field gradient, the strength of this interaction is not strong enough to, give you these splittings, okay? So this is the spectrum, okay? And then look at this experiment here, meaning if we record this, echo as a function of this tau, this other parameter, you basically obtain very different signal as a function of time that you can distinguish between the two situations. Actually, there is, clear mathematics, what you have to fit your data, and you can actually extract the value of nu q, okay? So meaning the strength of this term that it's quadratic in a spin number. So by symmetry, by playing with this pulse sequence, it allows you to distinguish what is, not just that whether you have magnetic term, magnetic coupling, whether you're coupling to electronic spin or to charge, but also once you work out all the machinery, it allows you to actually measure the spread in each one of them completely. So the noise, not just the absolute value of the thing like you would do in a spectrum, but to separate. And let me just kind of show you how it works. So again, this is a full calculation here of what happens in different. So let me just kind of walk you back. There are two terms in a Hamiltonian. So one is Zeeman, and so we can assume that it's a linear in a spin number, but this omega z is not just the absolute value of the frequency, but there is a spread, right? Electrons can be arranged in there could be a distribution of their spin number, okay? And that's what I call gamma z. Like, we just call it Zeeman noise, okay? We're using a language of quantum information. So the spread in the possible projections of the magnetic moments. And then there is also a possible, variation in these locally of these electrical field gradients in the material, of the charge distribution in the material, okay? And so I want to show you that what happens, okay? So for example, this is an example of a classic LMR spectrum. There are two cases, right? Usually what happens, well, I can have some magnetic noise, magnetic distribution of the magnetic properties, and that determines the width of my NMR line width. And then I have these electrical field gradients that are finite. You see, it's much larger, and then actually, that would cause this splitting. So I see multiple lines, okay? However, you can also be in a situation where, you basically have zero average electrical field gradient in your sample, but there is a huge noise, a huge variation in these quantity, okay? So huge inhomogeneity in a charge distribution or orbital distributions. But on average, everything is zero. And so what that would give you is this like really broad line, which you would never be able to discern in an experiment. And then, you measure a spectrum, and your spectrum basically just tells you about, magnetic distributions, okay, spin, okay, that's all. So let me show you now. Black is this scenario, red is this scenario. What happens when you do our, multi-dimensional spectroscopy, when you actually measure your echo as a function of that spacing between the pulses? Black, so first of all, if we have finite, so this is, this situation A. So if I have a finite quadrupolar moment, okay, so something real, what it would actually happen, it would cause these oscillations. That's what you would see in a signal, see? And then there is some kind of a step, and it decays, okay? This decay here comes from some magnetic decoherence, and then you see this oscillation here, if you analyze, corresponds to the splitting between these quadrupolar lines that you would see in a spectrum. So that's kind of nothing really new. The only thing that it allows you to do, if you do all the analysis correctly, it allows you to really separate that, what I call quadrupolar noise from the magnetic one, okay? But if we're actually in a situation here where, imagine that on average, my electrical field gradient is zero, but locally it's not. There's a huge distribution in the values. It's distributed so that the average is zero. It has kind of finite distribution. This is this black curve here. So my, quadrupolar or this coupling, okay, to the orbital degrees of freedom is zero. Actually, this is what you would obtain. You would obtain these black curves here. So look at this solid curve. And what is when you analyze this, it's this position of this step actually tells you exactly, you can use that to extract the distribution or the noise in these orbital degrees of freedom, the variation in space, even though the average is zero. And you can test whether you really predict your theory correctly, because the key here, why you can distinguish between the two, is that you control, when you apply that 180 pulse, you control, that kind of cancels all the noise from Zeeman, from something that it's time reversal symmetric, psi z, versus the square in the spin numbers. So by different amount pulses allow you, different length of the pulse allows you to refocus different parts by symmetry, whether it's linear or quadratic or any higher order, right? Even or odd in a spin interaction, okay? And that's what allows you to do that. And so what we can do is I can say, well, I don't have to apply the perfect 180. I can actually control, if I apply something stronger or weaker, I can control the amount of this refocusing. Okay, what is it that I want to refocus and cancel out of my measurement? And, what actually, this is a calculation. If I apply now, instead of a 90, 180 pulse, instead of 180, we apply. So we are actually controlling the amount of this inversion of or cancellation that we can refocus in, that we can induce, efficiency, right, of refocusing. And sure enough, what you actually find that moves the position, the height of this plateau. But it doesn't change the physics, meaning, the time at which this plateau tells you about the distribution width here, okay, or this noise, okay, in the orbital channel. And so, there are a lot of things that we can do theoretically. You can simulate, you can calculate things because it's such a, relatively speaking, simple calculation. And here it actually shows you it gives you kind of a roadmap to how to do the experiment and check what you're extracting is correct. And, these pretty pictures, okay, are basically telling you, depending on which of these, you never know in experiment from a spectra, what dominates. Is it a charge noise or a spin noise? And these are just different regimes. Different colors here just tell you different pulses, right? So how efficient am I in inverting this spin system? It basically controls how we do this, relative phase, how do we get information out of it? And, I know there's a lot of curves here, but we're actually able to measure this stuff in the lab by changing the pulses. And I'll show you this. And just putting it out there to show that, it's a very well-determined system. And even though it looks very complicated, you can actually tune these knobs in the lab and figure out really, what's going on or what dominates your system. And so let me now show you, there was a lot of theory here, how we actually apply this. And I'm going to go back to this kind of mess here, so a material, that's a formula. I won't even bother saying, but what matters here is that it's a Mott insulator. So it's a very strongly interacting system. Electronic interactions are very strong, and at the same time, it actually has strong spin-orbit coupling. So the energy scale actually, they are comparable. So nobody can do perturbation theory, and there's a lot of arguments of how to actually solve this problem. And why this material, it's been kind of a mystery, is that there's something very special about it. It started like in 2007, so a long time ago. People measure its magnetic property, and there was something really weird about how do you have a cubic system, but then it has this magnetization orients along the diagonal of the cube. That should not happen in very simplistic terms. And then, people actually knew that it orders magnetically, but then, if you measure specific heat, so just do, energy, if you measure specific heat, you find that there's a missing entropy. So, everything, if you do, calculations, you should find that all the effective spin should be 3/2 because of spin-orbit coupling. Nevertheless, what is actually measured here at this magnetic transition was ln of 2. So as if, basically, what is ordering is spin 1/2? So how does this happen, right? Where's the entropy? That should not happen, right? Big no-no. So, just to kind of give you an overview, we've been studying this stuff for a very long time. And, this is kind of what we knew about it from standard NMR is that, the system is in this paramagnetic state. It's an insulator. And then there's this green phase, which, you basically start to distort locally your cubic symmetry. So there's broken local point symmetry phase. That's very important because that tells you if you break it, you have to have these multipolar orders in orbital channel, okay? So there's some kind of these are predictions here of like what supposedly we expect for this orbital order should be, okay? And, but we have no proof of that, okay? So it's just a, maybe, yeah, we know that the cubic symmetry is breaking, and then suddenly you actually go into this. And then if you lower temperature even further, you actually form this magnetic state, and we figure out what that magnetic state is, okay? So let me kind of show you why we were not happy with what we, published or seen. So here, I don't know if you can see these spectra. I overlaid them, okay, here on this phase diagram. So if we're at, room temperature, 300 Kelvin, you get this super, super sharp NMR line. Basically tells you that, whoever made a crystal maker did an amazing job. It's super pure. It's like you can't even see it. It looks like we cheated. That's a delta function. That's how narrow this spectrum is, okay? And then, the only reason why we claim that there is this broken local point symmetry phase is that, well, we kind of saw when you lower the temperature down to about 13 Kelvin at 7 Tesla, the thing, your spectrum, right, it starts broadening. But that broadening could be anything, okay? And then, well, once you get here in the blue phase, then things are very clear because you get this splitting, and we know that splitting is, because we formed electrical field gradients. You cannot have a gradient if you have a cubic symmetry, so that basically tells you that your lattice deformed, okay? And again, we can do standard NMR and figure out, yes, it's orthorhombic distortions and so on and so forth. So, here we're happy, okay? The problem is this, right, the green stuff. So do we have multipolar, what is going on there, okay? And so, when your line starts broadening, you never know. Is it magnetic? Is it like there's no, you just don't know, right? You can claim whatever you want, but you're never sure. And so basically, our problem kind of, it's can we actually measure electrical field gradient, small electrical field gradients in the presence of Zeeman noise? In, to speak experimentalist language, can I actually resolve, right, what's going on here when, I can't because my spectra is just a Gaussian line, and I have no idea what is the origin of the broadening of my spectra, okay? We tried to do all the tricks of rotation stuff. It was not conclusive at all. It's just a mess, okay? And so let me show you now. I'm going to go back to, so, what I would like to do is I would like to know if this line, even though it's broad, actually has some, if there is, quadrupolar moments, if there is an electrical field gradient, or can I separate, because I showed you those very complicated colored, beautiful colored pictures, and I claim I can actually figure out how much is the Zeeman noise, how much is the quadrupolar noise, how much of the distribution of the two can I get. And so this is what we did. So the experiment is, again, that we actually, what I'm plotting here is the echo intensity that we measure as a function of this time now between the two pulses, okay? And look, at 300 Kelvin, this is a curve, this is 13, this is 15, 10.5, 5. So at 5 K, we just did it for sake of argument, right, is that you see these oscillations, this frequency actually corresponds to exactly this splitting here. So there's nothing really interesting there. And if you look at this theory curve here, these curves, so this blue one is basically this red, and red basically tells me I have a finite electrical field gradient, which we already knew. And if I analyze it, I can also extract how much of that distribution is in there, okay? But if you look at this black curve, that black curve has this plateau. And that's kind of what we see here, okay? So that basically tells me that I have, on average, electrical field gradient. This quadrupolar interaction, on average, is 0. But it has a finite width. And I can measure that width, okay? The frequency of that by actually, you see, by measuring the beginning of this plateau, okay? I mean, you do the fit into right things. It's not the same. But this, you see these red arrows basically tell you what is the frequency of this distribution, okay? And average is 0. And so, yes?
What happened to the 10.5 Kelvin below?
Here. You have to look at the time scale. It's a dead time of a spectrometer. You can't come any closer to that. Yeah. But let me show you that I know that this is not the artifact. So, at 13, you clearly see it. Here, we just couldn't. You basically use this to fit, and then you figure out the onset because there's a very well-defined theoretical form. And, of course, you can always be critical and say, oh, there are just two relaxation decoherence processes, right? So,
I just noticed the points.
Yeah, it's missing because of the dead time. If you look at the time scale here, look where it's a log scale here, and we're below 1 micro. Huh?
I should ignore the fact that there's a data point that's going downward.
Where? Here or here?
Yes.
But no, that's nothing. It's just a noise. Yeah. But let me show you this now. So this actually at 26 Kelvin, because it's just, then we can, the times are such that I can actually get the full curve. And, this is 380, so we went above, right? I just want to point out that, again, when we fit this into a theory, we were able to, extract this distribution. So orange corresponds to that. Every point that you see there is data. Every line is not the guide to the eye, it's actually a fit to a theory, okay? And then, so you can, for example, here we have done the full test as a function of tip angle or efficiency of this refocusing. And, again, all the curves are the data, what you expect from, the curves are actually what you expect from just doing simple quantum, dynamics, what you calculate the density, what you should expect. And the dots are the data. You can also rotate. You can do all sorts of studies as a function of tip angle and isotropy. Again, everything agrees. All the curves, as I said, is just what you expect from simple dynamics calculations. Just supposedly, it's just, again, a check of what we measure. It's truly what we believe it is. And again, you can see how narrow this line is at 26 Kelvin. And that brings me now to basically, when we analyze all the data, this is really what we did. All of this is to extract what, as I said, everything up prior to this blue phase, basically you have this interaction, this electrical field gradient, this quadrupolar interaction was 0 on average. And what we can extract is the noise, right? The width, the spread, the distribution of it. And you extract in real number, in kilohertz, right? In a spectral. And this is actually what we get. So you see these points. And what it's about, this is, so it starts about, 10 kilohertz. And what we see is that we have actually a significant spread, okay? I have red because this is it. And again, it's this quantity here, the coupling constant is 0. This just measures the spread in this interaction throughout the sample. And you see that it actually grows. It's present at 400 Kelvin, basically 380 Kelvin, well above room temperature. That's where missing entropy of the system is. It's just distributed in this, static charge disorder, okay, or orbital disorder. And, it kind of grows. And what is very interesting is as you're approaching magnetic phase transition, it actually, it's this static disorder that actually increases or blows. If I look into like standard NMR and look at the fluctuations, in spin, magnetic fluctuations, there's nothing at this phase transition, just a little crossover. There's no, increase, textbooks tells me that if I measure T1, spin lattice relaxation rate, at the magnetic phase transition, it should increase orders of magnitude. None of that. So this, magnetic phase is driven really by this kind of static orbital disorder, configurational entropy. And that's where all the distributed basically from 10 Kelvin up to 400. And I just want to, kind of give you a picture of what we think is happening physically, right? Because we have this. So this is kind of a cartoon of what we think is happening, that we have these local domains, orbitals. It's cubic. And so we can actually there are two things that define distortions, okay, from perfect cubic symmetry. It's this angle, and so angle is given this way, and also the magnitude of the distortion, and that allows you to actually define, say, order parameter of this phase. And, what we're actually showing here is that, these angle, if you can kind of see with your eye, of these rods, and the hue indicates this local angle of these distortions, and the length, it tells you about this, the magnitude of them. And the point of these graphics is actually to show that on average here, I have some distortions, but on average they're zero, okay? And they're not spatially uniform, okay? And I will end by showing you this. So black curve here is the noise. It's a magnetic noise, okay? My gray Hamiltonian, something linear in spin. Red is the noise in this quadratic term, okay? Orbital degrees of freedom. So if we plot them together, okay, you see that it's this orbital static disorder that drives this phase transition into a magnetic state. That's the only thing that blows. This is a log scale. There's a little increase in these magnetic log, but that's nothing as compared to this. And what is actually, once you go into this magnetic state, you see that this magnetic noise is the one that falls down, okay? And again, this is a log scale, so don't be fooled by it. What is actually curious is this orbital, this quadrupolar noise, is at the same level as it was right here. So what actually happened is that this static disorder, okay, drives this phase transition. We go magnetic, the spin orders magnetically, right? We have magnetic order. This actually just develops the finite electrical field gradient. It picks, kind of the preferred direction in space so that the finite electrical field gradient suddenly can be detected. But the noise, this, distribution or whatever, the variation in this is actually identical. So orbitals do not, they do not order. This, as Kemp put this, orbital glass or whatever it is that we're going to call this state remains, okay? And anyway, so I'll stop here. We're out of time. So to kind of show you, and just to, it was a lot of talk, but the point being, we can actually measure the distributions in quantity that, are on average zero, which means, no other standard technique can actually do that, right? If something is zero, you're not going to have a measurable quantity at all. Yeah. I'm done.
Questions? Yeah. Okay. Yeah.
Would it be easier to do an X-ray diffraction?
They see nothing. They see nothing.
Did measure the temperature dependence of the bipolar factor?
Locally, but
No, just from the broad.
you can't see it.
There's no effect?
No. Nobody has actually even seen this deformation in this material, which is really insane, You can't resolve it.
Because of
You shine the X-ray on your whole crystal. Yeah. And it involves oxygen too. So.
Just in this point of clarification, when you see noise, is this spatial noise or temporal noise?
This is static, so spatial, this strictly spatial. Yeah.
And so when it diverges like that, it's still not thermal.
No.
It's just that it's developing more and more difficult.
I mean, you measure fluctuations by temporal fluctuations by doing, T1, T2. There's nothing there.
I'm wondering, so the part of the mystery of this compound was that you were missing basically one
Mm-hmm.
structure, and the other one performs an order. And those two different limits of the spin-order coupling. Can you distinguish those two different limits?
Actually, Diba was very helpful on that. Because of the, you could actually knowing, right, I mean, yes, if I would write the whole, you should be able to distinguish actually. So the fact that you are, your, how do I say this? This quadrupolar term, right, or quadrupolar order picks up a finite value or preferred direction in this magnetic state that actually if you, for theorists like Leon Balance, if he writes, or Nandini, full Hamiltonian, that should be enough information for them to figure out which one of the two scenarios is the correct one. It's like, I mean, we don't know. Look, the point is, this is just like you ask a computer to put you something that it's on average 0, right, but distributed, and you put, there's more disorder, right, more variation, right, locally between this picture and that, right? But I have no idea on the size of these,
You can't see the size.
No. I can just tell you, by how much they vary,
You should have measured it by one factor.
Nothing. Yeah.
Gang.
Vesna, what is the hyperfine field in the magnetic order state? And also, what's the anisotropy? What is the spin orientation in the order state?
That's something we figure out long before. Let me see. That's what the hyperfine coupling is, and it's the units of Bohr magneton per Tesla. But the point being is that so the way the magnetic state is, if you see there are two sublattices. Okay, you see A and B, and this is kind of shows you each plane is ferromagnetically ordered, and they're actually staggered with respect to, it's about 70 degrees, 68 degrees to be more precise, with respect to easy axis, 1110 direction. And the funny thing is that, according to any theory, right, this is the hyperfine coupling in paramagnetic state. And when you order, this is what we found out from experiment. Every textbook tells you that this has to have the symmetry of your either crystal lattice or magnetic lattice. What we found to fit the data, is a mess. It has no symmetry whatsoever, which basically tells you that you must have some very complicated multipolar order something, right? And that's why it's such a messy hyperfine coupling tensor. But, we're working on being able to rework this backwards, right, and figure out from hyperfine tensor, but it's a very, tough job.
Okay, Jay.
I'll ask you a very naive question. I haven't thought about HVAC for 30 years. I can sort of, appreciate the effort you make of going over the physics concept I could almost follow without having to, chew the derivations. And so this one graph that you show, you have this whole temperature range. You show your measured data agree with theoretical prediction really well. At high temperature end with more sort of noise. So that's all intuitive to me. But like going back to one of the early curves, you showed this delta function at high temperature. What is the connection back to that?
This or something like this, you asking?
Yeah.
Well, that's the NM. The connection is just to show you how if I just do a standard NMR, I will learn nothing. It's just,
Is there
a Bohr.
reason why at high temperature there's whatever the curve supposed to be a delta function?
Because all the averages are 0, right? So everything is 0, and it's just you have just some very low, very small noise that comes from this two sources, okay? Magnetic, and it's a static noise, okay? And this charge distribution. And that noise is actually weak, it's mixed up. And the reason why, everything is so narrow here is just because the noise is small, but it's there. And because average of everything is zero, right? So when you average things to zero, if you do this kind of measurement, you cannot conclude anything. It's
Maybe the last question.
The only non-professor question is going to ask a dumb one. Few slides later, I think we will plot of a gamma Q as a function of temperature. I was wondering, is gamma Q a measure of the spread of the quadrupole moment?
yeah,
Okay, so,
of the quadrupole interaction, really of this term here in front.
right, so we're getting a wider spread as we go down in temperature.
Yeah.
So obviously the average is still different.
Okay, maybe I still ask the last question. Missing entropy was at low temperature or high temperature?
It's high temperature.
High temperature.
It's in this static distribution. Yeah. So it's distributed basically to 400.
It's real entropy.
Yeah.
You can count by states.
Yeah. No.
But it doesn't account.
That accounts, then everything is cool. We know where it is. Yeah. But we can count it.